In this lecture, we discuss data truncation or windowing. Now, anytime we have a set of data that has been stored in memory, we have to truncate or limit the length of the data, and this process is described as windowing. So basically, a windowing process can be thought of as multiplying the data by some shaped function. If the window is simply truncated, in other words, we start taking data at t equals 0 and we stop taking data at t equals some finite amount of time, then basically we have still windowed the data, it's just we've chosen our window shape to be rectangular. Now it's important to remember that multiplication in the time domain is equivalent to convolution in the frequency domain. So because we have windowed our data, in the frequency domain what we actually see is the convolution between the frequency spectrum of the window and the frequency spectrum of the data, and that's important to remember. So here's a visual of what we just discussed. We have some data record here, and we are only able to acquire that data for a finite period of time, and so effectively what happens is that we have a finite length of data, and this function is referred to as a rectangular window, and it basically is like multiplying the data by 1 for the length of the data record and 0 everywhere else. So once again, windowing is multiplication in the time domain. The signal is multiplied by the window. And this is like convolution in the frequency domain. So every point in the frequency domain is going to be modified by the frequency characteristics of the windowing function. So an ideal window would have a frequency spectrum that was 1 at 0 hertz and 0 everywhere else. What does that mean? That means that if you have a frequency characteristic of your signal out here, you would like for it to convolve with nothing. So the width of a window spectrum at 0 hertz is referred to as the main lobe. And the non-zero height of the spectrum away from 0 hertz is referred to as the side lobe. The wider the main lobe of the window, the less accurate is your frequency resolution, because nearby points are going to become averaged together. The higher your side lobes, the more adjacent frequencies influence the spectrum and become a part of the spectrum. So here's a rectangular window, and here is the FFT of this rectangular window function, showing you basically what the spectrum of the rectangular window looks like. So notice that it has a very narrow main lobe, but it has relatively high side lobes. So what this means is that these frequency characteristics right here of the window are going to mix into the frequency characteristics of your signal. But since it has a really narrow main lobe, your resolution is going to be good. So you're going to, using a rectangular window, you're going to have good resolution, but you're going to get characteristics of that window frequency spectrum mixed in with your signal spectrum. Now this is a Hamming window, so you can see the Hamming window. You have a little step, and then you have a little step of 0.5, and then you have a little functional characteristic given by, it's a cosine type window. So if we take our data set and we multiply it by a Hamming window, this is what it looks like on the output. So notice the zeroing out occurs more gradually than a rectangular window would do. This is usually what MATLAB defaults to, is the Hamming window. And it's considered to be a good compromise. So if we look at the main lobe, over here on the right, the main lobe is moderately wide, which means we're going to get some sacrifice on our frequency resolution. But notice these side lobes, and he's got a typo here, this should be side lobe. Notice these side lobes are considerably lower, so they have considerably lower magnitude than the main lobe. The Blackman window has even lower side lobes. They're down roughly 70 dB, but the main lobe is much wider, so that's going to cost us some resolution. Here's the function for the Blackman-Harris window, by the way, with typical coefficients given as shown. So let's look at what is in MATLAB. So MATLAB has a lot of different windows. This is the Chebyshev, the Gaussian, the Hamming, the Hanning, the Kaiser, the Triangular, the Blackman, and there are others. So in this particular case, we could window that waveform that's given in vector x by just using triang, the MATLAB command, and then that puts a triangular window onto x. And we can apply that window by multiplying. Actually, this one creates the window based on the length of x, and this one actually multiplies the window by the data set. So as an example, let's generate a data set that has two sine waves that are fairly closely spaced in frequency at 235 and 250 Hertz. Let's add some white noise, put that in a 128 point array and sample it at 1 kilohertz and create the signal to noise ratio to be minus 3 dB. And then we want to compare a rectangular, a Hamming, and a Blackman-Harris window to the signal and take the Fourier, or apply these windows to the signal and take the Fourier transform, and then plot the magnitude spectra. So we want to get an indication of how these windows are affecting our spectrum. So I'm going to let you read through these on your own, but basically the goal will be that we will define a sampling rate and a signal length. We'll use signal noise to add noise to the data. We'll generate a frequency vector so we can plot the spectra. We'll take the magnitude of the FFT output, or the signal with no window, in other words, a rectangular window. Then we'll use the Hamming routine and the Blackman-Harris routine. So here's the code. This will be uploaded into the folder containing codes, and here are the results. So you can see, applying the rectangular window, we have those two, the 235 and 250 components are very clearly evident. You can also see, though, that you have this kind of odd addition to the spectrum. So if we look at the Hamming window, we can see that we can still resolve that there are a couple of peaks here at 235 and 250. Once we go to the Blackman-Harris window, we're beginning to get smoothing out here on the noise. And, you know, this frequency spectrum in this area that looks less like a rectangular window spectrum. But notice that we've lost our resolution between the 235 and the 250. So there are some issues that show up. If your window smooths too much, you lose the resolution of your data. But if it doesn't smooth much at all, then this noise out here, it becomes a little ambiguous. Is this noise, or are these data peaks here showing up? And you won't really know unless you do some things looking at the application of different windows to the data set.